Alright, this is the second example of chapter 9.2. It is question 199. Let's read the question. Question 199. A 600 nanometer light fall on a photoelectric surface. An electron with the maximum kinetic energy of 0.17 electron volt are emitted. Determine A. The work function. B. The cutoff frequency of the surface. C. What is the stopping potential when the surface is illuminated with light of a wavelength of 400 nanometer. So let's write down the two pieces of information we are given. We are told that if we flash a light with a wavelength of 600 nanometer, the maximum kinetic energy will be 0.17 electron volt. All right, for part A, we need to find the work function. Now it's useful to know what is the individual energy of each photon, as it will be used in the formula after that. So to find the individual energy, we have the Planck constant multiplied by the frequency. Now remember that lambda multiplied by the frequency is equal to the speed of light. Therefore, frequency is equal to speed of light divided by lambda. We get an energy of 3.3 multiplied by 10 to the power minus 19 joule. In electron volt, this is 2.07 electron volt. All right, so we need to find the work function. So we will use that formula. It's not exactly the one we've seen previously. I switched the Kmax on that side to isolate right away the work function. And once we plug in the value in electron volt, we find that the work function is 1.9 electron volt. It is also equal to 3.04 multiplied by 10 to the power minus 19 joule. We will see that we often need this value when we want to figure out the cutoff frequency. Okay, so that's it for part A. Let's do part B. So part B, find the cutoff frequency of the surface. Now, the cutoff frequency is the minimum frequency needed to extract the electron from the metal. So it's happened when the kinetic energy of the electron is exactly 0. So we got the work function is equal to the Planck constant multiplied by the cutoff frequency. So we simply have to isolate the cutoff frequency, and we get a cutoff frequency of 4.6 multiplied by 10 to the power 14 hertz. Now let's go to part C. Part C, what is the stopping potential when the surface is illuminated with light of wavelength 400 nanometer? So again, we need to go back to this formula, and we are looking for the stopping potential. Now the stopping potential is linked to the maximum kinetic energy. So therefore, we isolate the maximum kinetic energy. It's equal to the charge multiplied by the change in potential, and we call this the stopping potential. It is equal to h multiplied by the speed of light divided by lambda. Now here, that term will be in joule, okay? Minus the work function. Now, if we have that term in joule over here, that means we need to convert that one also in joule, all right? Now, just to be sure we are clear here, I'm gonna erase the upper part. I just wanna make sure everyone is clear on how we do that computation. If you need to pause the video, do it now. Write down the relevant piece of information, and I will erase part A and B basically. Actually, just A. I still need these data. So let's see how we could compute everything in joule here. So we got stopping potential is equal to H. So H is 6.626 multiplied by 10 to the power minus 34 multiplied by the speed of light, 3 multiplied by 10 to the power 8. We need to take the charge and divide it on these two terms, and we also got the wavelength over here. So the wavelength, we are told, is 400 multiplied by 10 to the power minus 9. The charge is the charge of the electron, so it is minus 1.6, and we will see the answer. The final answer is minus 1.2 volt, and the minus come from the charge of the electron here. Multiplied by 10 to the power minus 19, and we got the work function in joule divided again by that term. And we combine everything, we get a stop voltage of 1.2 volt. All right, so that's it for question 199. Let's go solve another example.